Okay, welcome to my channel. My name is Solo Ange, and in this video we're going to do this integral right here. In a previous video we did something that looks quite similar, but of course they are not the same. That one had a plus, this one has a minus, and this minus makes a big difference, and you're going to see. Okay, so let's see. Well, though along the line we are going to still apply the rule which we used the last time. A lot of people call it the King's rule, that when we have a definite integral where the bounds of integration are just numbers, then we can write this wherever we find the independent variable, we can write it as the sum of the bounds of the integration minus the variable. That in this case is going to be tangent of pi minus x. But do we really need to use it from the beginning? Well, you can go ahead and try that, okay? But I'm not going to do that here. So let's see what I'm going to do. Well, I'm going to start off with the fact that tangent is sine over cosine. So maybe let's rewrite that function a little bit. So I'm going to come down here because of the light, okay? So let's observe that. It reflects and it will not show what I'm writing. So let's see what we get. This is the integral from 0 to pi over 4 of the natural logarithm of, well, since tangent is sine over cosine, I'm going to write this as cosine of x minus sine of x, okay, divided by the cosine of x, and that is just by adding the two fractions, 1 over 1 minus sine over cosine. This is what we're going to have. Okay, so from here I'd like to split the integral into two, using the fact that the natural logarithm of the difference of the natural logarithm will give us the natural logarithm of the ratio. So I can write this as the difference of the natural logarithms, and I'm going to use that the same step to split the integrals. So this is going to become the natural logarithm of the numerator, which is cosine of x minus the sine of x. Okay, then I'll put the dx right here, then minus the natural logarithm of the denominator. So minus, let me bring it down here, minus the integral from 0 to pi over 4 times the natural logarithm, okay, of the denominator, which is cosine of x dx. Again, that's built into the fact that when we have the difference between natural logarithms, it will give us the natural logarithm of the ratio, and this is the ratio right here. Okay, maybe let's give these integrals names. Maybe I can call this I1, and then I can call this I2. Okay, so I'm going to start off with I1, so that maybe with time we can bring in the I2. So let me put the I1 down right here. So that is the integral from 0 to pi over 4 of the natural logarithm of the cosine of x minus the sine of x. Well, notice what we have. We have cosine of x minus the sine of x. Well, after so much work, okay, I want you to observe or to think about this as either sine of multiple angles or cosine of multiple angles. Well, think about the sine. Sine of a plus b, that is a plus b in brackets, will give us sine a cosine b. Okay, if this was plus, then it will be plus cosine a sine b. If it was a difference, let's say sine of a minus b, that would be sine a cosine b minus, okay, cos a sine b. So you think about this as there is nothing here. Maybe the sine of the angle is missing, and then the cosine of that same angle is missing, and that could be maybe because that thing was factored out. So if it was factored out, then the thing must have been equal. Well, sine of which angle will give us equal results? Well, in the first quadrant, that is when the angle is acute, that would be 45 degrees, which is something as pi over 4. And because sine of pi over 4 is root 2 over 2, and then cosine of pi over 4 is also root 2 over 2. So what I'll do here is to multiply each of these terms by that factor, and I'm also going to divide it. So let's see, multiply this by the root 2 over 2. That means you're going to have root 2 over 2 times the cosine of x, then minus the square root of 2 over 2 times the sine of x. Good. Well, maybe let's make this bigger. Okay, so we're going to we've multiplied that. Now let's divide the root 2 over 2, which we just multiplied, and I can divide that by multiplying it by 2 over root 2, which is the reciprocal. Okay, great. So we notice that that is what we have, and then we can put the dx right here. So let's reiterate. Well, when we have sine of pi over 4, that gives us root 2 over 2. Then again, cosine of x minus cosine of pi over 4, that gives us root 2 over 2, then sine of x. But since this root 2 over 2, since it was not here and it was not here, what I've done here is to multiply the outside by 2 over root 2, so that when we distribute, we get back to what we started with. That's just for the I1. Sorry, this should be I1. Okay, great. So let's see. Good. Okay, so doing that, let's see what this will leave us with. Well, I can still use the natural logarithmic property or logarithmic property that logarithm of the product is the sum of the logarithms. And this will give us the integral from 0 to pi over 4, okay, of, well, let's take the natural logarithm of, so you notice from what we just explained that this right here is sine of, okay, sine of pi over 4 minus x. So let me put it down here, sine of pi over 4 minus x. Good. So the pi over 4 accounts for the root 2 over 2. Okay, and then, yeah, taking that as a sum, that is plus the natural logarithm of square root or 2 over root 2. Good. Then maybe we can put the dx down here. Alright, so what we've just done there is to take that the natural logarithm of the product, where this is the first part of the product, and then the second part is just the root 2 over 2 part. Is the sum of the natural logarithms, and that's what we have. So let me put it up a little bit. Okay, so this becomes, well, this right here is just, we can split the integrals. Notice that the integral of the sum, where the sum is finite, is the sum of the integrals. So in this case, we're going to have the sum of that. But, sorry, the integral of that, okay? So integrating this over the x variable, where this is just a constant, we're going to get, this time the upper bound, which is pi over 4 times the natural logarithm of 2 over root 2. Okay, that's nice. Then we add it with the integral of this right here. So we're going to add that with the integral from 0 to pi over 4. Hope that's showing. Okay. From 0 to pi over 4 of the natural logarithm of sine of pi over 4 minus x. Okay. Here, maybe let me point out the rule which I stated from at the beginning of the video. That when we have the integral, maybe let's say some function of t dt, let's say from a to b, this right here is the same thing as the integral from a to b of the function, but in this case, we're going to rewrite the argument as a plus b minus t. Okay? Okay, great. And then we can put the dt down here. That is the rule I was talking about. Okay, that means from left to right or from right to left, the equality holds. That's all that matters. So in this case, we can think about this as from right to left, where the integral is from 0 to pi over 4. If I add 0 to pi over 4, I'm going to get pi over 4. Then I subtract x from that. So that means that's the same thing as saying sine of x. So in place of that, I'm just going to put in sine of x. And that is due to that rule. So let me just clean this and put sine of x. Okay, great. So that's the natural logarithm of sine of x. And that's what we get. And then we put the dx right here. Okay, the original integral, which I'd like to say I, okay, good. The original integral, which I'd like to say I, is, so the I here, that one makes sense. Okay, we remember that I had to split it into I1 and I2, where I1 has given us this. So, writing the original integral, we're going to take pi over 4 times the natural logarithm of 2 over the square root of 2, that is the constant part, sine of x dx, then minus I2. So this is that, then minus I2, which is the integral from 0 to pi over 4 of the natural logarithm of cosine of x, and then you put the dx right there. Great. Okay, so with this, I'm going to combine these two integrals. And we notice that this is going to be the integrals, okay, from 0 to pi over 4, from 0 to pi over 4 over the x variable. So we can combine the natural logarithms. That will be natural logarithm of sine of x minus natural logarithm of the cosine of x. Okay, so we're going to use some logarithmic properties on that. And that will give us, let's reduce this. Well, 2 over root 2 is the same thing as square root of 2. Yeah, so let's work with that. Okay, so I'm going to add these two integrals. And notice that natural logarithm of sine of x minus the natural logarithm of cosine of x is the same thing as natural logarithm of sine over cosine, which is natural logarithm of tangent of x. Good. So that is it right there. And then we can put the dx right here. Okay, so we have to work with this. So maybe I can give this a name I3 because this will require a lot. Okay, so let's start off with the I3. Good. So you notice we're going to add this constant in the end. So in case I forget to add, you just add it for me, alright? Good. So let's see what we can do. Well, I'm going to start off with a u sub. So for the I3, I'm going to say let y be the tangent of x. So I'm going to call the inside y. Good. So doing that, that means that the derivative of y with respect to x will be, well, when we differentiate this gives us secant squared of x. But secant squared is something as 1 plus tangent squared. So that will be 1 plus tangent squared. But y is called tangent squared. That will be 1 plus y squared. And then you put the dx right here. So that means that the dx right here will be replaced with the y over 1 plus y squared. Meanwhile, the tangent of x will be replaced with y. So that means I3 will become, maybe there's no point putting it down, but let's just write it. That will be the integral. Well, the bounds of integration as well will change. So when x is 0, what happens? Tangent of 0 is 0, so y will be 0. Then when x is pi over 4, tangent of pi over 4 is 1. So yeah, the top there will have 1 as y. Good. So this is the natural logarithm of tangent of x, but we've replaced that with y. So that will be tangent of natural logarithm of y instead. Then the dx is dy divided by 1 plus that. So let me rewrite it. dy divided by 1 plus y squared. Okay, so maybe you still have a little room. And let me just use this room to remind you. I know some of you have not forgotten, but it's just something we'll have to make use of. That will be the geometric series. You notice that when we have the sum, let's use r as our index, as r starts from 0 up to infinity of, let's see, x raised to the power of r. Okay, this right here gives us 1 plus x squared plus x cubed and so on and so forth, where the first term is 1 and then the common ratio is x. Okay, and that is a case where the absolute value of x is less than 1. We'll have this to be 1 minus x. Good. But notice what we have down here. We don't have 1 minus y. Rather, we have 1 plus y squared. And that would be the case where this x is negative y. And when I'm saying this x, I'm not actually talking about this. I'm just using this for something else. Maybe I should have used a different letter. But it doesn't matter. Okay. So we are going to rewrite this using this property. And you're going to see how we're going to do it over here. So let me just clean some part of this and then we'll continue. Okay, so after cleaning that and recalling this property right here, this right here must have been from the sum of something. And in this case, the common ratio here is negative y squared. And the square does not affect the negative. So with that, I'm going to rewrite that as the integral from 0 to 1. So you notice that from 0 to 1 of the natural logarithm of y. Okay, that is the natural logarithm of y. Good. Now the 1 over y squared before the dy. So let me put the dy right here. So for the 1 over y squared, I'm going to write it as the sum. Maybe let's use r, as r starts from 0 up to infinity. It's an infinite series of, let's see, negative y squared. That's how it's going to be. Good. So that in this case, it's not just x, where we'll have, if x is replaced with negative y squared, that will be negative of x, but in this case, negative of negative y squared. That will be 1 plus y squared. And that's exactly what we have here. So in this case, we assume the common ratio to be negative y squared. Great. Okay. So let's see. This is raised to the power of r. Sorry for that. So this is y squared. All right. Okay, so we have the dy. Good. So let's see what we can do. Well, and this is true when, let me put it out for you. This is true when negative y squared, which of course is the absolute value of just y squared, is less than 1. And we can accept that here because this y, in this integral, y ranges from 0 to 1. So we're going to look at a case where it approaches 0 from the right and it approaches 1 from the left. Therefore, y is not exactly 1. So the absolute value of that is strictly less than 1. And we can make use of that infinite geometric series. Okay, so using the convergence of that geometric series, the absolute convergence of that, we can switch the integral sign and the summation sign to get the sum as r starts from 0 up to infinity of, maybe let's rewrite this. So notice that I can write this, I can peel this negative 1 off, so that we have negative 1 raised to the power of r. Maybe let's bring the integral in to handle only the y terms. So that will be the integral from negative 1 to 1 of the natural logarithm of y. Let me put the y power first. That will be y raised to the power of 2r. That is built into that. Then the natural logarithm of y dy. Okay, great. Now we're going to apply integration by part on this. So this will give us the sum as r starts from 0 up to infinity of negative 1 raised to the power of r. Okay, so let's use the integration by part on that to see what we get. Okay, so by integration by part, I'm going to integrate y raised to the power of 2r, and I'm going to differentiate the natural logarithm of y. So maybe we would integrate this. This gives us y raised to the power of 2r plus 1 divided by 2r plus 1. We multiply with the natural logarithm of y. So this is y raised to the power of 2r plus 1 divided by 2r plus 1 times the natural logarithm of y. Then we subtract, okay, from the rule, all right? Integration by parts in the integral of maybe u dv equals to uv minus integral of v du. So that will be the integral from 0 to 1. Okay, so we're supposed to evaluate this from 0 to 1. Okay, so the integral from 0 to 1 of, maybe let's differentiate this and then multiply with the integral of that. But notice that that will give us y raised to the power of 2r plus 1, because this gives us 1 over y when we differentiate. And the 1 over y times that, will reduce the power from plus 1 to just 2r, okay, divided by 2r plus 1. This is right here is dy. Okay, so first we'll have to evaluate this right here. Remember, it is not actually when y is 1, but rather when the limit as y approaches 1 from the left. That is the limit as y approaches 1 from the left. So notice as we approach 1, natural logarithm of y will be approaching 0. And then this is going to be constant. So that means we're going to have 0 when we are approaching 1. So this will be 0. Then minus when we are approaching 0 from above. Well, natural logarithm will be approaching negative infinity. Meanwhile, this will be like 0. So that is more like a 0 times infinity kind of indeterminate form. So we need to evaluate that limit. But let's do it real quick right here. I'm going to please permit me to use the L'Hopital's rule. So we're going to take the limit as, let me say, y. Let me use red for that. Okay, good. Let's do it real quick. So that will be the limit as, let's say, y approaches 0 from above of this right here. Now, this constant does not matter. So let's just take the function. Well, I'm going to write this as, this is natural logarithm of y. This y to the power 2r, I'm going to put it down and then put it down again. Okay, just to rewrite the fraction, that will be 1 over y raised to the power of 2r plus 1. So by division of fractions, this is exactly that. But of course, I've excused the constant a little bit. Okay, so I'm going to apply the L'Hopital's rule on this, like I said earlier. When we apply the L'Hopital's rule on this, this should be the limit as y approaches 0 from the right of, let's see what this will give us. Well, when we differentiate this, that will be 1 over y. We differentiate this, that should be negative 1 over 2r plus 2. We will multiply top and bottom by y raised to the power of 2r plus 2. That should give us y raised to the power of 2r plus 1 divided by 1. But clearly, as y approaches 0, this right here approaches 0. The denominator is just a constant. That means that the limit is 0. So this limit right here is 0 as you approach 0 from the right. Good. So that wasn't really an important part. You can do that on your own, but we just needed to show. So I'm going to clean it off. Good. So let's continue. So this gives us negative. Well, this right here, everything here is just 0. So this right here breaks down to 0. leaving us with this negative term. But this is the negative, the integral of that. So this right here is pretty easy, just using the inverse power rule. We add 1 and then divide by the new power. This means this is going to give us the sum as, let's say, r starts from 0 up to infinity of negative 1 raised to the power of r times this. But this has a negative sign, so maybe let's build up the power of that negative 1, because this negative 1 will join with that, right? Good. So then when we integrate this, we'll have y raised to the power of 2r plus 1. That is by adding 1 to the power, then divide by the new power, which is 2r plus 1. But there is a 2r plus 1 here. That will become 2r plus 1 squared. And this right here is very nice. Okay, so recall what we had. Well, we had to stop here. Okay, so we have to add this constant to this right here so that we have the original integral. That's as a solution. So permit me to clean this right here. So I'm just going to say that this integral is equal to pi over 4, then the natural logarithm of square root of 2. Well, I can think about the square root of 2 as 2 raised to the power of 1/2. I can factor it out front. That'll be pi over 8, then the natural logarithm of 2, then plus, okay, plus this sum right here. That is plus the sum as r starts from 0 up to infinity of negative 1 raised to the power of r plus 1, then times this part, which is y raised to the power of 2r plus 1 divided by 2r plus 1 squared. And this right here is a good place to my black pen, red pen, sorry, my Michael pen. So we're gonna stop here. Okay, hope everything is showing. Alright, okay, thanks for watching. I hope you enjoyed this video. Please do well to subscribe to my channel, Solo Ange. Alright, share this video with your friends, and of course we'll continue for my next video.